To welcome the gathering, allow me to invite Dr. Jaya Jacob, Junior Scientist, Kerala State Council for Science, Technology and Environment.
Respected dignitaries on the dais, distinguished scientists, fellow researchers, students and esteemed guests, it gives me immense pleasure to warmly welcome all of you to this very special session honoring the winners of the Kerala State Young Scientist Award, an award that truly celebrates scientific excellence, original thinking, and meaningful contributions to society through research and innovation. Today, we are very proud that we could felicitate two outstanding scientists whose work reflects the true spirit of recognition, rigor in research, and relevance to national priorities and the promise of shaping the future in science. We warmly welcome Dr. Anjita Vishwanath, scientist at ISRO Inertial Systems Unit, Thiruvananthapuram, whose work on indigenous inertial navigation and precision sensing technologies has played a vital role in major ISRO mission, including the reusable launch vehicle, landing experiments, and the Gaganyaan test flight. Her ongoing research on quantum inertial sensors and energy harvesters further strengthens India's future space missions. A warm welcome, Dr. Anjita. We are also privileged to have Dr. Shankar P., Assistant Professor, Department of Mathematics, Cochin University of Science and Technology, a mathematician here with us whose research in functional analysis and operator theory deepens our understanding of complex systems with strong relevance to quantum physics and modern mathematical analysis. We look forward to insightful presentations from both of you, from both our awardees, and to engaging discussions, especially to the young researchers here. We would request you to have a very meaningful discussion with the examples of young scientists right in front of you that will inspire you in your scientific journey ahead. Once again, a very warm welcome to our distinguished speakers. Also, a warm welcome to Dr. Deepthi, who has been organizing and coordinating this program. And we invite you all to a very insightful session ahead. Thank you.
For the presentations, I now invite Dr. Shankar P., Assistant Professor, Department of Mathematics at KSYSA.
Hello, yeah. So, good evening, good afternoon all. I would like to thank KSYSA for awarding me this Young Scientist Award. So thank you very much. So now we want to see, actually I am a pure mathematician, pure mathematics doing guy. But somehow I want to convince this to the public that whatever I am doing, that is relevant to the public. So I will try to make more mathematical, and for anyway there will be a mathematics will come, we cannot avoid that. So we will see what is this invariance of space problem. Actually this is an open problem, still this is not solved. If you solve this, so you may get some bigger award in the mathematical community, you will get the recognition. So before going to explain what is this problem, so I want to explain so that by the known word. Suppose you assume that like you have some live concert is going on. So when your live concert is going on, there will be a lot of musical instrument they will play. So when they play musical instrument, then you have vocals, guitar, drums. So then including that you will have crowd noise also. So there will be a crowd noise also. But with all these things, suppose your mic captures all these things and deliver all these things, this will be total messy. So total messy, you will not get anything clear. Okay. So for that what we need, we don't want the noise. So that means the mic or whatever that is you are having observer, it will take a messy signal, but then we don't need the same messy signal output. we need a clear whatever we need, like suppose you vocals, guitar, the limit we need the output. So there where the operator comes. So you can take C. So that is a thing, this is what invariant subspace says. So you don't want any noise, but you need poor vocals, you need clean guitar. So then maybe there will be lot of instruments. Some instruments you need some level. Okay, so some music, some level. So for that you maybe drums, if you don't want, you make it as a 0. I think these things you can consider as a subspaces. Okay, as a set or something, only pure vocals. So that means whatever pure vocals with the limit I am having, that is to come as a output, and the clean guitar also come as a output. Okay, so for that I will take those things as a subspace. So whatever I don't want that. That means when the mic should capture the power vocals, then that should convert them into vocals only without any noise and any other disturbance. So that's where your subspace comes. Okay, so that's where your subspace comes. So you need an operator or subspaces like this. Yeah, so that is the thing. You consider these vocals, guitar, drums as a subspaces, and before you are doing this equalizer, like you will have noisy only, but after doing your equalizer you will get poor vocals and clean guitar, all these things. So does this audio operator T preserves musical subspaces? That is the thing. Suppose you consider all the music instrument. So the question is now invariant subspace problem became whether it can preserve, it can take vocals to vocals, guitar to guitar, all these things. Okay. So this is how this will do. Yeah. So yeah, this will do because we can make, so you forgot about, if you know Hilbert space, it's not a problem. We can consider Hilbert space. So that means you consider full instrument as a one space, then all these vocals and the guitar as a subspaces. I need a operator, so equalizer, so that it makes your messy signals to the clean signals. Okay. So this is a, like, if you want, you can understand it very clearly with these applications. So that is the thing you need. So this is in the signal processing also. Even not only here, maybe you can take a transmitter. So if you want, you are watching TV, you are receiving mobile, all these things are there. But when you are in mobile, internet also you are using, you need same kind of things. Like whatever exhibited from there, you should receive the same thing, then only you will get a poor correct signals. Okay, some messy things we should not want. Okay, that's where the key invariant subspace problem comes. So then this kind of spaces we have. So here also we will have some technical terms are there, so I cannot avoid it. Anyway, this Berling subspaces, and you will have some composition operator. So this thing I will come to this one. Yeah. So what is this? So first we will try to understand, this is a mathematical slide. So you take an RD space. So RD space, you will have an integration representation also, you leave out. But you can have a sequence, like you take a sequences. So you apply F, then you go like this, then you can have this H2D. That means you take a sequences, you just sum it over, and so that the coefficients AN has to be square summable. So then your Z has to be from where? It is from the unit disk. Suppose you have a plane, you can take a disk from this. So this is called RD space. Yeah. So yeah. So then you have a RD space. So now we are going to have a subspaces of those RD spaces. So then we are going to have a lot of operators between them, lot of operators. So there, whether that operator can have a invariant subspaces. That is the question. Yeah. So now you take this multiplication operator. You can define F going to F psi. Just you multiply with some function. So that is the thing. Yeah. So you have this multiplication operator, and yeah. So what Berling proved. So this is a very old problem. So it's solved in 1948. What he proved that if you take an RD space, you take a multiplication operator by only mz. You are multiply whatever function is there only by z. So then you can find an invariant subspace for that. Okay, not only one invariant subspace, you can find all the invariant subspaces. Okay, so because of this one operator, the invariant subspace problem for this operator is solved. Okay, so if you take this, again I am repeating, you take a RD space and you consider multiplication operator by Z, so then all the invariants of space, not only like this all the invariants of space will look like your theta h2, where theta is an inner function, some kind of function. Okay, so this, after this result only people started looking at invariance of space problem. So these things you can again relate it to your audio system and transmitting signals, all these things. So here what you need, you have a function, then you will have a music and you will have a noise also, but I need only music, I don't need noise. Okay, so then your theta h2 you can consider, and the theta h2 perp also you can consider, that also you can write as some theta n is h2. So you want to remove the noise, only you want music. So that means that this MP3 keeps only your music and it discards the noise. Okay, so this is the thing. So this was the application in MP3 compressions. Okay, so now, so what is invariance of space directly? So this is a mathematical thing. So you have an operator, bounded linear operator, you take a Banach space. So yeah, so in the Banach space, if you take any subspace, so then that it is called invariant, then the operator T should map to itself, T of Y subset of Y. Okay, so the invariant subspace problem is this one. Does any bounded linear operator on the Banach space as a closed invariant subspace? So this is a general question. If you take any operator as a non-trivial closed invariant subspace or not. So there are fewer for Banach space setting, there are different spaces are there in mathematics. So you can take Banach space setting, the answer they found actually for some cases for finite dimensional and for non-separable case and normal operator and all. But there are counter example also. So there are some operator where you cannot have this invariant subspaces. Okay, so then you can take some L2 space like the n-flow proved something. So but what is there actually, the crux is there in the Hilbert space, this problem is still open. If you take an Hilbert space, so Hilbert space is nothing but an inner product space. You can, so only the advantage of studying inner space is if you take a one space, you can consider orthogonal complement of that one. The other space will be, you can orthogonal complement, you can write that one, that is a inner product, that has a geometry, more geometry it has. So that is the thing. The question is, if you take a bounded linear operator on the infinite dimensional separable Hilbert space, that has a closed invariance of space or not. Okay, for some cases it no, but it's not proved generally. But this problem translated into a finding a minimal invariance of space for your hyperbolic automorphism for the composition operator. If that all the minimal invariant subspaces are one dimensional, so then you can say that this invariant subspace problem has a solution. But this is a equivalent criterion, but it is not still solved. So it is there. Yeah. So now, yeah, what is composition operator? This is thing. You take unit disk D. So that means you take a complex plane. In the complex plane, you take only unit disk. So composition operator is defined as C phi of F equal to F composition phi. So but what are the other application of this invariant subspace problem is, it has a stable quantum states and control theory, dynamics and PD signal processing, everything it will be applied. Yeah. So now what happened? So what happened in the case of, anyway for our multiplication operator, we have certain things using still now whatever we are having this mic and everything, by known operator they found this thing. But if you want more clarity, more thing, you want to solve for more operator. If you take composition operator, if you solve this invariant subspace for the composition operator, then you will get some better versions of these preservers. Okay, in the real life application also. That's what we are going to do. So this composition operator will take you to the clean music. But the problem is, for the composition operator also, for some cases only it is solved. The problem is often for most of the cases, like for phi. Okay, even this is not, we are not trying for general subspace. We are taking a subspace of the type theta h2. The theta h2 is a invariant subspaces of multiplication operator. So that is the thing. Yeah. Okay. Yeah. So now this is the question now. So whether for what kind of phi the theta h2 will be subset of theta h2 itself. Okay, so what are the phi such that C phi of theta h2 for theta h2 itself for the self maps phi. Yeah. So so you can take, I used theta, the theta is a inner function. So inner function means is geometry. You take a unit disk, in the unit disk it takes interior to the interior and boundary to boundary, that's the thing. So this, even this inner function, you can, the example is the Blaschke product and this singular inner function. So Blaschke product means it will have a 0, that means it will vanish if you substitute z of a in theta of z, so it will be 0. Okay, so it will, but if you take a singular inner function, it is a non-vanishing singular, non-vanishing inner functions. But these are the two examples, then what are all the inner functions? So you can write all the inner functions will be of this one only. This is a product, all the inner functions will be this product of Blaschke's and only singular inner function. These are the things will come. So the singular inner function will not have any zeros, but Blaschke product will have a zeros everywhere. So that is the thing. So that ANs are, you can consider as a zeros. Yeah. Okay. So then these are some of the known results for the Blaschke product. You can able to find the invariant subspaces. So yeah. So for the Blaschke product, you can able to find some previous known results these are, but we don't want to go into that format, but that what we did here. So we were only looking at the problem, it's raised by Matache. So he told that if you take two measures mu1, mu2, maybe now we can focus not only the same space invariant, you take a one space and apply the operator whether it can go to different spaces also. Okay, so in between two different spaces, you find an operator, it takes this space to the another space. So that is the question. So here, he gave for the non-vanishing function s mu1, this is a inner function, whether C phi of s, this s mu1 h2 subset of s mu2 h2. So this is the thing. So this question he told, but this we cannot able to prove this directly for all this, but whether the equivalent condition you can able to give, whether some kind of measure theoretic equivalent condition you can able to give for the solution of this one. Yeah. So this one you can, so we found that not only for the singular function, you take, if take any inner function, if theta 1 HP, subset of theta 2 HP, then this quotient theta 1 composition phi by theta 2 belongs to bounded analytic function. It is a bounded analytic functions. So that's what we proved. Then we got some corollary using those things also. So as a this thing. So then what we did for the Blaschke product also, we got some multiplicity criteria. So suppose you take C phi of B1, because this B1 is a Blaschke product, it has zeros. So the multiplities of zeros of B2 will be less than or equal to multiplities of zeros of B1 composition phi. So then this is equivalent to say that C phi B1 HP subset of B2 HP. So that is the thing. Yeah. So similarly for if you take phi, so phi also you can vary for automorphism. So what we did, so if you take an automorphism, you can write, so this you can write what? If you take any inner function, you can make separate this thing, Blaschke and shift operator. Okay, so you because any inner function is a product of Blaschke and the shift operator to singular function. So Blaschke and the singular function. So Blaschke product and singular function. So then you can separate them for only phi is automorphism. If you take non-automorphism, you cannot able to do that. So for that we have an example here. So this is little bit, we have to do mathematics. So little bit technical. So I am leaving this. We can have an example. If you take non-automorphism for this phi, so then you will have examples such that this theorem, this result may not be true. Yeah. Okay. So now, yeah. So this is the major thing. So what we gave, suppose you take two different inner singular inner functions. So then S mu1 HP subset of S mu2 HP. So then we proved that we can give a measure theoretic characterization of this one using mu1 and mu2. Okay. That measure of the mu2 of E, the measure of the function S mu, like the mu2 E will be always less than or equal to mu1 pi of E. So for the elliptic automorphism with fixing 0, this some kind of special automorphism, otherwise you can say this automorphism. So this result, using this, we can give more elaborated version. If you take a automorphism, you take disk to disk, it has a fixed point anywhere in the disk. So then we can prove that this invariant subspaces to different subspaces using this measure theoretic characterization, this number 3 measure theoretic characterization, using that we can do. So this is the thing we did with this paper. So the first paper you can see, this appeared in Journal of Mathematical Analysis and Application in the Elsewhere journal. So this is with my PhD student and my one of the collaborator, Muthu Kumar. So my main thing is that this has a applications in your voice cancellation and sending the signals to, so TV signals, even mobile signals. Only as an example I gave for this musical instrument, but you can everywhere this kind of thing is applied. Okay, thank you.
Thank you, Dr. Shankar. I now invite Dr. Anjita Vishwanath, scientist and engineer at Indian Space Research Organization, for her presentation.
So, a very fine good afternoon to all the respected dignitaries on and off the dais and all dear delegates of the 38th Kerala Science Congress. So first of all, with immense gratitude, I take this as a privilege to present my contributions in engineering, indigenous inertial and quantum sensor technologies for India's space missions. So I'm a scientist engineer SE and I belong to Sensor Electronics Division, Advanced Sensors Group, ISRO Inertial Systems Unit. So about my background, I'm basically an electronics and communication engineering graduate from KSYSA, optoelectronics and laser technology postgraduate again from KSYSA, and after that I have done PhD in Earth to Satellite Free Space Optical Communication Links from IIT Delhi. And after completing my PhD, I have joined ISRO as scientist engineer, and now I continue my journey with ISRO. So to start with, the motivation behind my work is simple, but a powerful reality. Whatever may be the space mission, the success of the space mission depends upon the accuracy of the inertial navigation sensors or the inertial navigation systems. Whether it is Chandrayaan making a precision soft landing, or Gaganyaan ensuring the safety of the crew module during its ascent and re-entry, or an RLV, reusable launch vehicle, gliding back autonomously into Earth, it is the inertial sensors which are the silent decision makers. So, the success of a space mission depends upon the inertial sensors or the accuracy of the inertial navigation systems. So spanning from the development of robust inertial navigation sensors and fast and accurate navigation algorithms, I also dwell upon the design and development of electronic systems for the next generation quantum inertial sensors as well as sustainable energy harvesters for long duration planetary missions. So this is not just a scientific pursuit, but in fact it is a vision to build indigenous, high precision and future ready sensors to enable India's strategic space missions. So to start with, if you take any inertial navigation system, the core of the inertial navigation system is the ISRO ring laser gyroscope. It is the most important angular motion sensor that is used to measure angular rate in all our launch vehicles and spacecraft. Unlike spinning mass gyroscopes, inertial navigation, this ILG, it basically has got an optical cavity in which you have two counter-propagating laser beams. and there is a frequency difference between the two counter-propagating laser beams, which directly gives you the measure of angular rate. So that is how the ILG functions as an angular motion sensor. So figure F4 shows the basic schematic or basic diagram of the ILG ring laser gyroscope, and the principle behind ILG is called the Sat-Nag effect. As I said, the two paths, counter-propagating paths, will have a frequency difference that is directly proportional to the angular rate. And that phenomenon is called Sat-Nag effect, which is illustrated in figure F5. Now, what is the challenge in realizing this ILG? As seen in figure F6A, you can see for lower rotation rates, what happens is that these two counter-propagating laser beams couple to each other and you really do not get any output. You can see for a rate less than 833.467 degree per hour, you have a dead zone. Although you have an input, you really do not have an output. And that is not how your sensor should be working. So we have to address this lock-in problem. And what is the solution for it? Dither. Dither is a sinusoidal rotation which is coupled to the body of the ring laser gyroscope through a piezoelectric transducer, and what dither does is that it moves your gyro body to and fro with a very high frequency. But still you will have dynamic lock-in zones at crossover frequencies, and that is what is shown in figure B for rates less than 20.5 degree per hour. So our objective or our problem to address is this lock-in phenomenon to improve the stability, reliability as well as yield of the sensor. So as said, we have to overcome the problem of dynamic lock-in, the zero zones or the deadband zones at the crossover frequencies. So what you have to do is that you have to randomize the amplitude of the dither signal. So figure F7 shows the work in which I have patented the optimum dither random noise ratio, for which you can reduce the bias instability value to 0.015 degree per hour, which means you will have a really very good accuracy in your navigation. Now moving on to figure F8, you can see an automated threshold monitoring and control system which I have developed and ISRO has inducted into the production line of ILG. More than 100 sensors have already gone through this setup and it has improved the reliability to 92.3%. So here what we do is that we keep on monitoring and controlling the threshold voltage of ILG, which is one of the most important health monitoring parameter of ILG. So these are one of the two major contributions as far as sensor development was concerned. Now, moving on to the algorithm part of it. Once you have all the sensors, you have the system, you need to have the algorithm to do the navigation. So as I said in the very beginning, the accuracy of the navigation system depends solely on what is your initial orientation. So for you, to start this navigation, you have to know what is the initial orientation with respect to a reference coordinate frame. And once you obtain this initial orientation using the sensor data itself without any sort of external aid, you call that alignment self-alignment. So here, what is the criticality or what is the importance of this self-alignment algorithm when it comes especially to reusable launch vehicle as well as Gaganyaan missions is that there is no other way out, there is no other external sources available for you to achieve the initial orientation other than to develop this sort of an algorithm. So this algorithm was developed for the first time, and it was developed because of the criticality, the need for the accuracy in obtaining the initial orientation. So what happens if there happen to be initial alignment errors? See, if there happen to be initial alignment errors, it can lead to attitude errors during launch, your trajectory will deviate, and finally, your orbit insertion can itself go wrong, which can lead to mission failure. So that is the criticality of this problem. So your objective is to develop a new fast and accurate self-alignment algorithm where you really do not have any sort of external sources other than your sensors to find out the initial orientation. So here figure F9 shows the block schematic of the newly developed fast and accurate self-alignment algorithm. So before implementing this algorithm into our upcoming missions, we have to prove this algorithm in previous mission data. So figure F10 shows the assessment of this alignment algorithm in the historic Chandrayaan-2 mission data. So from this plot, you can find it is having a very fast convergence, which is even less than 100 seconds, with a very high accuracy, both in terms of azimuth as well as level angles. So having proven the accuracy and the fastness of convergence of the newly developed algorithm, this algorithm was implemented in reusable launch vehicle landing experiments, mission 1, 2, 3, as well as Gaganyaan TVD1 missions. So the mission, all these missions have successfully proved the algorithm we have developed. So now, moving on to the work what I'm currently focusing on, IISU is intending to build quantum inertial sensors that rely on the wave nature of ultra-cold atoms. So when you come to ultra-cold atoms, we have the wave nature wherein we'll be able to do interferometry, and that interferometry principle is used for sensing as illustrated in figure F13. When it comes to the sensitivity orders, when you move to the quantum nature, where you have the quantum nature of atom as the principle, you have a very improved accuracy in comparison to classical sensors as illustrated in this table. When you take an accelerometer, if your conventional sensor can measure 10 to the power minus 6 G, your quantum sensors can measure 10 to the power minus 10 G. When it comes to a gyroscope, if your conventional sensor can measure 10 to the power minus 2 degree per hour, your quantum sensors can measure up to 10 to the power minus 7 degree per hour. I basically focus on the electronics development, the indigenous development of electronic systems for these quantum inertial sensors or quantum inertial systems. So basically, like in a very, very simplified way, this is how the block diagram looks like. To the science chamber, we have the laser system, its electronics, control loops, then we have the detection electronics as well as a pulsing circuit which is required to ensure the complete synchronization. So this is in a very, very simple level, that is a block diagram. And in this, we have the extended version of this is the intensity stabilization loop, which is shown in figure F15, and the performance of the loop is shown in figure B. And 6 is an optical phase lock loop. Because in interferometry, we need Raman lasers, and we have to ensure the phase coherence of the Raman lasers. So for that, we have the optical phase lock loop, and this is the experimental setup for OPLL, and this is the block schematic. So these are the work which is being currently going on from my side. And to an advanced R&D area, I also focus on the development of sustainable energy harvesters for long duration interplanetary missions. So to start with, we have the Mars lander mission. So in Mars, as characterized by NASA's environmental assessment compatible meter, what happens is like in Mars, you have frequent strong dust storms, which characterizes the electrostatic building in atmosphere of Mars. So our idea or our concept is like, what if we use as abundant available mechanical and triboelectric or electrostatic energy in Martian environment to harvest energy which can be used to power sensors which are used for planetary exploration. And these are called triboelectric nanogenerators. And it basically works on the principle of contact electrification and electrostatic induction as shown in the video. So we have a response project on this, and figure F18 shows the first prototype of the energy harvester, and figure B demonstrate a contact type triboelectric nanogenerator which can be incorporated into the wheel of the rover to harvest the energy. So, concluding upon the social relevance and tangible research output for the past 8 years of my work in ISRO, I basically focus on building indigenous capabilities in precision sensors, navigation systems, as well as triboelectric nanogenerators and cold atom interferometry based quantum inertial sensors. I hold an Indian patent in ILG, and I have around 16 publications with over 230 citations, and I lead 2 major ISRO projects, one for developing the complete laser system for next generation quantum inertial sensors, and 2 for developing triboelectric nanogenerators for Mars lander mission. And most important part of my work is like the algorithm which I have developed is already being flight proven and qualified for all our reusable launch vehicle missions as well as the upcoming Gaganyaan missions, the human rated space flight missions. So to conclude upon, all these which enable the precision navigation sensors, pioneering triboelectric nano generators, as well as advancing cold atom interferometry based quantum inertial sensors, it all contributes and empowers to our nation's space mission with precision, reliability, sustainability, and self-reliance. So thank you one and all. Once again, thanks a lot for having given this opportunity. Thank you so much.
Thank you, ma'am. To conclude this session, may I invite Dr. Deepthi B., Junior Scientist, Kerala State Council for Science, Technology and Environment to deliver the vote of thanks.
So respected dignitaries, invitees and awardees, a good evening to all of you. So as we come close to the KSYSA presentation, I would like to extend my sincere gratitude to the awardees, Dr. Shankar P., Assistant Professor, Department of Mathematics, KSYSA, and Dr. Anchita Vishwanath, Scientist at ISRO, for their insightful presentation and for sharing their research experience with us. So let this award provide you the pathway for securing more awards in future for your research contribution. Thank you. I also extend my gratitude to Dr. Jaya Jacob, Junior Scientist at KCST, for the warm welcome and for introducing the awardees. Thank you, Dr. Jaya. Okay. So I will also like to acknowledge the continuous contribution of KCST, the organizing committee of 38th Kerala Science Congress, and the technical team for the smooth conduct of this program. So thank you all for participating in this lecture. Thank you.
Thank you, ma'am. Students who have not yet registered for the lectures will have the opportunity for a spot registration. Code will be displayed at the end of the discussion and it will also be available at the registration desk. We will now have a small tea break. Please join back in 15 minutes.